Yeah, sure. Okay. Yeah. Thanks for inviting me to give this talk. And for those of you who don't know me, so my name is Jian Kang, and I'm currently a PhD candidate at UIUC, working with Dr. Han Tong. And yeah, I'm happy to share some of our recent efforts in algorithmic foundation of fair graph mining. Okay, let's get started. So we will start with a very common observation that the graphs are everywhere in our daily lives. So for example, the collaboration networks can model the collaborations among the researchers, and also the chemical compounds can be represented as molecular graphs, and also many infrastructures can also be represented as graphs, like the road networks or power grid. And also some other typical examples of graphs include the brain networks and knowledge graphs. And because of the ubiquity of this graph data, so it is very important to dig out the useful information with the graph mining algorithms. And in the past decades, so many graph mining algorithms have been developed and applied in different application scenarios, such as the credit scoring, the financial fraud detection, smart city, and so on. And in general, most of these graph mining algorithms are designed to answer these who and what questions. So for example, what is the most important or most relevant web page with respect to a given user query? And to answer this type of who and what questions, so we often follow a very simple pipeline where we have an input graph, and then the input graph will be fed into some graph mining model, and then the mining model will output the mining results. So let's see this very simple toy example of loan approval. So suppose we have some a network of the loan applicants as shown here, and then we will apply a node classification algorithm on this network. And as a result, this algorithm will classify each applicant as approved or not approved for the loan. However, if we consider the gender of each applicant and assume that this the male and the female has a similar credit history on average, then we can see that male actually has a higher approval rate than female. And as a result, we can conclude that this classification result is unfair because male has a higher approval rate. So, and this kind of unfairness in graph mining results can have a very severe consequences in many real-world applications. So, for example, if the online community is biased with respect to the political view of its members, then it may further cause problems like the hate speech, hate crime, or polarization. And also, this unfairness could also cause problems in many other applications, like the ranking and recommendation. So to avoid this situation, a key question we want to answer in my research is how can we make the graph mining process and the graph mining results to be fair? And in order to answer this question, so it is essential to propose a paradigm shift from answering this who and what question for graph mining to understanding the how and why for fair graph mining. For example, some typical examples include how do the graph mining results relate to the input graph, and why does the graph mining results is unfair, and how to ensure the fairness in graph mining. And to achieve this paradigm shift and build an algorithmic foundation for fair graph mining, we envision that there are four essential properties, including the utility, fairness, transparency, and robustness. So for utility, it is actually a very common requirement because we always want the graph mining algorithm to achieve a good performance on the downstream task. And also, as we can tell by the name of fair graph mining, so fairness is another fundamental and important property to ensure the fairness in the mining results. And the third and fourth property are the transparency and the robustness, which are useful to the fairness as well because the fair graph mining models can be used for safe critical applications like the financial fraud detection or in some applications in the healthcare domain. So it is essential to call for these properties to enhance the trustworthiness of these fair graph mining algorithms. And specifically, for the third property, it corresponds to the transparency, which aims to make the graph mining transparent by understanding how and why a model makes a specific decision. And finally, in terms of the robustness, we want to make sure that the fair graph mining algorithms are resilient to the noise, uncertainty in the data, or adversarial activities, so that it can be really applied to the real world, it really deployed to the real world. And given these four essential properties, the key challenges to ensure these properties naturally lie in the tensions among them. So we believe there are three main challenges, including the auditing challenge, the debiasing challenge, and the safeguarding challenge. So the first challenge is the auditing challenge. It actually considers the tension between the utility and the transparency. And for example, let's see this example of loan approval again. So we want to audit why a model makes a specific decision to some certain loan applicants. So key questions we want to answer is, what is the implicit relationship between the graph mining results and its input graph? And the debiasing challenge here considers the tension between the utility and the fairness. So for example, the results on the right, on the left are accurate, but they are unfair because male and female has a different acceptance rate, while results on the right are fair, but they are not accurate enough because we are giving loan to some applicants who should not receive the loan. So it is important to achieve a good trade-off between the fairness and the utility for fair graph mining. And the last challenge is the safeguarding challenge. So it actually considers the tension among all this desired property, which is critical to the deployment of these debiasing techniques in the real world. So for example, in the real world, it is naturally to have some malicious users that can attack these graph mining algorithms on purpose so that the model would make a wrong decision or a biased decision. So by addressing this safeguarding challenge, we want to make sure that the fair graph mining algorithm is robust to this kind of malicious users. And it can also explain why a model makes certain decisions to ensure the trustworthiness of the fair graph mining algorithm. So here I showed an overview of my current research focus. So in general, my research aims to achieve a fair graph mining by a paradigm shift from answering the who and what questions for graph mining to understanding the how and why for fair graph mining. And to achieve this goal, building upon the properties and the challenges I just mentioned, we aim to solve three tasks, namely the auditing task, the debiasing task, and the safeguarding task, which correspond to the three challenges I just mentioned. So in the next part, I will mainly focus on our recent efforts in the auditing task and the debiasing task. And the first work I'm going to talk about studies the uncertainty quantification for graph neural networks. So in this work, we mainly study the uncertainty quantification for graph convolutional network, or the GCN for short. And here I will give a very simple review on how GCN works. So basically, its key idea is to iteratively aggregate the information from each node's neighborhood, which is this so-called graph convolution operation. And mathematically, it can be represented as iteratively apply this equation in the middle of this page. And in many graph mining tasks with the graph convolutional networks, it is intuitive to observe uncertainties in the model predictions. So for example, in this toy example, the green and the blue nodes actually represent the label nodes of two different classes. And during the test phase, this node 5 compared to other nodes like the node 2 or node 8, as shown by the different colors, is more difficult to be predicted since it is closer to the two nodes with two different labels. So its predictive uncertainty will be higher than the uncertainty of node 2 and node 8 in the downstream task. And with this observation, we're interested to answer the following two questions. So first, we want to quantitatively understand the uncertainty of the GCN predictions. And we will term this problem as the uncertainty quantification on GCN. And second, we aim to improve the GCN predictions with the help of the quantified uncertainty, which is referred to the application of this uncertainty quantification. So a good thing is that there are already a few existing works that studies the uncertainty quantification on graph neural networks. And basically, there are two main type of approaches. And the first type is the Bayesian neural network based, which adaptively drops the edges. And but a key limitation of this kind of approaches is that they cannot explicitly quantify the uncertainty of the model predictions. And another type of method is called the deterministic quantification based, which aims to estimate the posterior by introducing some parameterized distribution as the prior distribution. And although this type of methods can quantify the uncertainty explicitly and deterministically, it will change the training procedure because of the additional parameters or additional architectures in the graph neural networks, which will further increase the model complexity and might hurt the generalization of the graph neural networks. So in this work, we want to know whether we can quantify the uncertainty deterministically without changing the GCN training procedures. And to answer these questions, we formally define this problem as shown in this page. So basically, given an input graph, a GCN with a task-specific loss function, we want to estimate the uncertainty of GCN predictions in a post hoc manner. For example, in this toy examples, with the input graph and the GCN, we want a simple plug and play module after the GCN so that we can quantify the uncertainty of each node in the graph without changing the training procedure of these GCN models. And our key idea to solve this problem is to quantify the uncertainty from the frequentist perspective rather than the Bayesian perspective. And the intuition of this frequentist perspective is to see how the model predictions would change if we change the training set by removing a training node. Then we can construct a confidence interval for each node with a Jackknife estimator called Jackknife Plus, which can provide provable theoretical guarantee on the exchangeable data. And note that in this work, we assume that the graph is an exchangeable data because when we shift the order of the node, the joint distribution of the nodes will not change, which is a common assumption in many works for graph neural networks. And with this frequentist perspective, the more confident a model is, the smaller the difference between the upper bound and the lower bound of that confidence interval. And thus, we can naturally use the difference between the upper bound and the lower bound as the uncertainty of that node. So here in this page, I will give you a very simple example of how this Jackknife estimator called Jackknife Plus works. So let's see this example. So in an IID data, so suppose we have a training set with 5 nodes with 5 data points and a test set with 1 testing point. Then we further assume we're training a regression model. Then we will first perform a regular training, and then we can obtain the vanilla prediction on this testing point. And then after that, by leaving out 1 training point at one time, then we can get 5 different predictions for the testing point, as well as the predictions for the left out data points. Then for the next part, we will construct the two sets to calculate the upper bound and lower bound of the confidence interval. And these two sets are represented as the P plus and P minus here. And then finally, we can find the quantile of these two different sets, which construct the confidence interval. And the upper bound and lower bound of the interval actually correspond to the two numbers in the orange as shown here. And then with the confidence interval, we can calculate the uncertainty score of that node to be 0.7, which is the difference between these two numbers. But the key limitation of applying this Jackknife plus is that we can see in this step, we need to, once we leave out a data point, we need to retrain this model again in order to obtain its predictions on the leave one out data. So we're wondering how we can efficiently estimate the parameters without retraining the model from scratch. And our solution to this efficiency problem is to leverage the influence function, which estimates the change in the model parameters with a first order Taylor expansion. And the influence function can be actually calculated as the multiplication of the inverse of the Hessian function and the derivative of the objective function. And in the paper, we also show how to efficiently calculate this this Hessian tensor with respect to the model parameters. And with everything ready, so here I will show the overall algorithm of a proposed method named JuryGCN. And we will first, so basically for each training node, we will first evaluate the influence with respect to it, and then compute the leave one out prediction as well as the residual errors once we leave out a node. And then we can obtain the two sets where we can find the quantiles to get the lower bound and the upper bound of the confidence interval. And finally, the algorithm will generate the confidence interval for this specific node and then calculate the width of the confidence interval as the uncertainty score. And in the next few slides, so I will show how we can utilize the quantified uncertainty to further improve the GCN performance. And basically, we will show two key applications. And the first application is active learning on node classification, in which our goal is to select the most informative nodes to query. So with this selected informative nodes, we aim to achieve a good classification accuracy on the remaining nodes, and we aim to improve this process by using our quantified uncertainty. And here, the key a key step in this active node classification is to design an effective strategy to select the most informative nodes. And here, with our quantified uncertainty, we will select the nodes with the largest uncertainty score as the most informative nodes. And from this example, experimental results, we can observe that our proposed JuryGCN can achieve the best query performance at different query steps. And we can also improve the performance of the semi-supervised node classification with the quantified uncertainty. So basically, in semi-supervised node classification, we commonly use this cross-entropy loss as the objective we want to optimize, where each node specific loss is simply averaged in the cross entropy. However, for some nodes that are very difficult to classify, so compared to the large quantity of these easily classified nodes, the loss value of these hard examples will actually have a very minor contribution to the final loss, which make it more difficult for the model to learn the useful knowledge for these hard examples. So in this work, we refer to the idea of focal loss and introduce a scale factor named beta for the loss of each node. And this beta factor is defined as the normalized uncertainty of a specific node U over all these training nodes. And when the uncertainty of the node U is larger, then the coefficient beta is also larger, which can outweigh the specific loss for a better training. And here we can consider two different cases for this beta factor. So first, if node U is misclassified and the corresponding predictive probability is small, then the uncertainty would be large, and the beta factor can increase the loss value. And the second case is that if the node U is well classified with a very small uncertainty, then the loss value will be downweighted, so that since the model has already captured a very useful knowledge for this easily classified nodes. And with our newly designed objective functions, we conduct experiments on the real-world networks. And from the figures, we can see we can get two key observations. So first, in terms of the classification accuracy, our proposed method has the best overall performance. And the second, we can see that as the number of the training node decreases, the gap between our proposed method and the other baseline method becomes larger, which means that the proposed uncertainty aware factor, which is the beta factor, can achieve a better performance when we have a few number of the training labels. So as a mini summary, in this work, we use the Jackknife resampling to estimate the node uncertainty from frequentist perspective. And then we also leverage the influence function to further improve its efficiency. And in the next part, I will introduce two works on the debiasing task. And the first work I'm going to introduce studies the individual fairness on graphs. So to introduce this work, so we will first look at the graph mining algorithm from an optimization perspective. So basically given a input graph A, a mining model with some parameter theta that can output a mining results named Y. Our goal is to learn this mining results Y by optimizing a loss function defined over these three terms. And here are three classic examples of the graph mining models that falls into this optimization perspective and will be studied in this work. And these methods include the PageRank for graph ranking, spectral clustering for graph clustering, and the first order line for graph embedding. And note that although we only study these three methods in this work, our developed debiasing methods are actually general and could be applied to any other graph mining algorithms. So in this work, we mainly aim to answer three research questions that are how to measure the bias, and given the bias measurement, how to enforce the individual fairness, and also what is the cost of enforcing this individual fairness. So for the first problem, which is so-called informed measures problem, its specific settings are as follows. So basically, given a graph mining model, a pairwise node similarity matrix, and some tolerance parameter epsilon, then we want to understand how to determine if these graph mining algorithms are fair or not. And in addition, we also want to have a quantitative measure of the individual bias in the graph. And to solve this problem, we follow a very general principle of the individual fairness, such that similar nodes should receive similar outcomes. And mathematically, this principle can be translated into this inequality shown in the middle of this page. And the intuition of this inequality is that if the similarity between two nodes is very high, then we will have a very small upper bound on the right-hand side, which will in turn push the mining results of these two nodes to be similar with each other. But to guarantee the individual fairness with this inequality, such inequality should be satisfied for all the node pairs in the graph, which could be too restrictive in many cases. Because for a graph with n nodes, then we will have the n square number of the constraint to be satisfied. So in this work, we actually consider a relaxed criteria by studying the overall individual bias for all the node pairs in the graph. And with such relaxations, the left-hand side of this inequality naturally becomes to this trace term with respect to both mining results and the Laplacian of this similarity matrix. And the right-hand side of this term, of this inequality naturally becomes to a single constant term. And with that, we can define that for graph mining results Y, it is individually fair if this trace term is no larger than half of this delta tolerance. And with this definition, this trace term naturally becomes to the overall individual bias measure for the graph, which actually measures the overall squared difference of between the mining results among all the node pairs, weighted by their corresponding pairwise similarities. And now that we know how to measure the individual bias, we would like to enforce the individual fairness by solving this informed algorithm problem. And in general, our goal is to learn this debiased mining results such that it can minimize the task-specific loss function as well as the individual bias measure at the same time. And to design this debiasing methods, let's take a look back at this graph mining pipeline. So we can see that in this pipeline, we have three key components which correspond to the input graph, the mining model, and the mining results. And naturally, we can mitigate the bias in each part as well, which leads to the design of this three different debiasing algorithm named debiasing the input graph, debiasing the mining model, and debiasing the mining results. And the first work I'm going to introduce is called debiasing the input graph, and it aims to mitigate the bias by learning a new topology A tilde that is close to the original topology, graph topology A, with the minimum number of the individual bias. And this goal can naturally lead to this bi-level optimization problem, where this green term ensures the consistency between the debiased graph topology and the original graph topology. And the orange term here is the individual bias measure we just talked about. And for this bi-level optimization problem, we further explore its KKT condition to reduce it to a single level optimization problem. And with such exploration, then we developed a method that is similar to the block coordinate descent to alternatively learn the mining results Y and also update the new topology A tilde by the gradient descent. But the problem here is how we can compute this, the gradient of the loss function with respect to the debiased topology. And to compute this gradient with respect to the new topology, we get the results as shown here. So we can see that a key component in this result is this large matrix to be calculated in the orange box. And our focus here is to design methods to efficiently compute this large term in the orange box, which we will call it the H matrix in the next few slides. So a good thing is that for all these three graph mining tasks we mentioned before, we can efficiently calculate this H matrix in linear time and linear space. So for example, for PageRank, this H matrix actually has a rank 1 structure, and for each vector shown in the shown as the green vector and the yellow vector, they can be calculated with linear time and linear space with the power method. And similarly, for the spectral clustering, the H matrix has a low rank structure as well. And for each vector here, we can efficiently calculate it with a low rank eigen decomposition in linear time and linear space. And again, so for the first order line, So although the math here looks a little bit complicated, we don't need to worry about it. So basically, with some vector and matrix operations, we can still calculate the H matrix with a linear time and linear space. And now we come to the second method, which is the debiasing the many model method. So basically, it aims to mitigate the bias during the model optimization by adding this individual bias measure as a regularization term in this entire optimization problem. And this problem can be solved by two different strategies. So the first one is a general solution, which uses this stochastic gradient descent-based optimization techniques to minimize the loss function. And a good thing is that it only needs a additional linear time to compute this gradient for this individual bias term. And in addition, we can also have a task-specific solution that can be applied to a specific graph mining algorithm. And the detail of debiasing the three graph mining models we talked before are listed here. So basically, we will not go into details about each method, but a short summary is that for PageRank and the spectral clustering, we designed a specific solver that runs the mining algorithms on the augmented graph as shown in this red box. And for the first order line, we use the general solution to optimize it with the stochastic gradient descent. And now we will introduce the third method, which is called debiasing the mining results. So it aims to directly mitigate the bias in the mining results in a way that is agnostic to the input data and the mining model. And mathematically, it can be formulated as this optimization problem in the middle of this page, where we want to achieve the consistency between the vanilla mining results and the debiased mining results. And at the same time, we also want to mitigate this individual bias measure. And fortunately, this optimization problem is convex as long as this regularization parameter alpha is non-negative. And the closed form solution of this problem can be obtained by calculating this linear system, which can be solved by many existing linear system solver like the conjugate gradient or the power method. And here we will talk about the third research problem, namely the informed cost problem. So we aim to understand the cost of enforcing the individual bias by analyzing the difference in the mining results with and without the fairness consideration. And in the following analysis, we are particularly interested in the third method, which is the debiasing the mining results method, because it's a model agnostic one. So here we show the cost of debiasing the mining results. And we can see that this upper bound shown in the middle of this page is related to several factors. And actually, this upper bound can be further controlled due to the low rank structure of many real-world networks, and also with some proper normalization on the adjacency matrix, which reduces the largest singular value of this matrix. And here we show the effectiveness in mitigating the individual bias with our proposed method. And we can see that our proposed method is effective in mitigating the bias while preserving the performance of the vanilla algorithm with a relatively small changes to the original mining results. So to summarize, in this work, we have developed a quantitative measure for individual bias on graphs, and we have also developed the three bias mitigation algorithms, as well as a theoretical understanding on the cost of enforcing the individual fairness. And in the next part, I'm going to introduce another work in the debiasing task that studies the degree-related fairness on graph convolutional networks. So let's first have a quick review that the GCN learns the node representations by iteratively aggregating this feature information from the neighborhood of each node, where the this so-called graph convolution operation is shown can be represented as this mathematical equation. And although the GCN is a classic one and its learning paradigm has shown the promising results in many learning tasks, it actually has its own problem that they often reveal an unfair performance among nodes with different degrees. For example, in these two examples, this node has a higher degree, which often enjoys a better recommendation quality for graph-based, GCN-based recommender system. While for this grassroots users in this recommender system, the system might provide some arbitrarily bad performance for this grassroots users, since it doesn't contribute much training data for this graph-based recommender system. And what is worse is that due to the long-tail degree distribution of many real-world networks, the GCN often achieve a good performance by benefiting this few numbers of the high-degree nodes, while overlooking the performance of many low-degree nodes like these grassroots users. And there are actually already some works trying to mitigate this degree-related fairness. And their general idea is to infer the degree-related information by introducing additional learnable parameters or additional components during the model training. But due to these additional parameters or the components, they often cost more computational resources and even change the architecture of the GCN to mitigate the bias. So we aim to understand how we can mitigate the degree-related unfairness without hurting the scalability of the GCN and without changing the GCN architecture. So different from this previous works that infer this degree-related information, we view this utility as a resource to allocate, and we want to find a fair allocation of the utility. For example, originally we may have an unfair allocation of the utility as shown by the black bars. And what we really want is that after the debiasing, then we want a fair allocation of the utility as shown in these orange bars. And to define such fair allocation of utility, we resort to this Rawlsian difference principle, which is designed to find a just allocation of social welfare to achieve the fairness. And here we can treat this utility as the welfare we want to allocate. And the least fortunate group here is the group of nodes with the worst utility, which also correspond to the nodes with low degrees. And based on this intuition, we aim to find a well-trained GCN such that it can minimize the task-specific loss and also achieve a fair allocation of the utility. And to find where the allocation is fair, we take a different strategy by understanding its stability of the stability of this Rawlsian difference principle. So basically, we achieve the stability when there is no least fortunate group, which means that all the group will have a balanced utility. But the bad thing is that for many utility measures, they're actually non-differentiable. For some classic non-differentiable utility measures include the accuracy or the F1 scores. And to accommodate this non-differentiable nature of the utility measures, we use the loss function as the surrogate measure of the utility, because we often want to minimize the loss in order to maximize the utility. And with this slight reformulation, our goal naturally becomes to balancing the loss of nodes with different degrees. But a natural question you may wonder is, we're minimizing this empirical loss during the training. So ideally, each node should have a small loss because we want its average loss is a small number. But then why do we still have a varied loss after the training? So here we aim to theoretically understand why the loss will be varied after the training. So by looking at how GCN is trained, we can see that the gradient is actually the key component in optimizing the model parameters. So we're wondering whether such kind of unfairness or the varied loss is possibly caused by the gradient with respect to the model parameters. And our short answer for this question is yes. So given this A hat matrices, the gradient with respect to the model parameters can be actually written as the matrix multiplication of these three different matrices. And with some mathematical derivations, the gradient can be further written as the linear combination of the node influence matrix weighted by the node degree in A hat. And such degree in this A hat matrix is actually positively correlated with the degree in its original graph, meaning that a high degree node in the original graph is likely to have a high degree in this A hat matrix as well. And with this high degree in this A hat matrix, when we do the linear combination, we can see that the overall direction for updating the model parameters will favor this high degree nodes because it is actually more closer to the high degree nodes in this space. And in addition, note that there are two different formulations of this gradient with respect to model parameters. One corresponds to the column sum of this A hat matrix, and one corresponds to the row sum of this A hat matrix. So in order to mitigate the impact of the nodes, we aim to normalize this A hat matrix into a doubly stochastic format whose row sum and column sum are always 1. And then with this doubly stochastic matrix, we can calculate a fair gradient without the impact of the node degree with using this doubly stochastic matrix. And guided by the computation of this fair gradient, we can use two different strategies to mitigate the unfairness, namely a pre-processing method called RawlsGCN-Grad and an in-processing method called RawlsGCN-Grad. So let's first look at the pre-processing method RawlsGCN-Grad, and its key idea is to normalize this A hat matrix into a doubly stochastic format first, and then feed this doubly stochastic format matrix into the GCN for model training. And for the in-processing method RawlsGCN-Grad, we will compute this. We will first compute this doubly stochastic matrix first, but then still use the original graph as the input of this GCN model. But the different thing is that during the backpropagation, we will use the doubly stochastic matrix to compute this fair gradient and then backpropagate this fair gradient to update the model parameters. So from this effectiveness results, we can see that our proposed RawlsGCN achieved the smallest bias. And interestingly, by mitigating the bias, we can sometimes improve the classification accuracy significantly because the model can achieve a much higher accuracy for this low degree nodes. And in terms of the efficiency of this RawlsGCN family, we can see that our proposed method actually has the same memory cost as the GCN and a much shorter training time compared to all the baseline methods as shown here. So as a short summary, in this RawlsGCN work, we analyzed the mathematical root cause of this degree-related unfairness in GCN through its gradient with respect to the model parameters. And then we proposed two different methods that mitigate this degree-related unfairness without additional cost in both running time and memory consumption. And in the next part, I will quickly go through some of our current ongoing research and our thoughts on the open challenges to safeguard fair graph mining. So the first work is about fairness attacks on graphs. So in general, it aims to attack the fair graph mining model to make it biased, but still achieve a high utility on the downstream task. And note that prior works either attack the utility instead of the fairness, or study the robustness of this mining algorithms against the random perturbations. And actually, there are very few works in this direction so far. So it is very important to understand the possibility of these fairness attacks and how we can achieve the attacks as the preliminary to study the robustness of these fair graph mining algorithms. And the second direction aims to ensure the fairness on graph mining algorithm in consideration of the uncertainty. So from this toy example, we can see that the mining results are fair with the existence of this uncertain edge. But if this uncertain edge does not exist, essentially, the mining results will change and eventually becomes unfair due to the decrease in the male's true positive rates. And to avoid this situation, we need to answer two research questions that are: what is the implication of this uncertainty in terms of the fairness on graph, and how can we achieve the fairness on graph under the uncertainty? And the last work aims to make the fair graph mining algorithm explainable. And the existing explainable graph mining methods only provide explanation with respect to the model utility, while many fair graph mining techniques are still black boxes to the end users. So to enhance the trust of these fair graph mining techniques, it is critical to design a post hoc explainer to provide faithful explanations in terms of the model fairness. So finally, let me conclude this talk. So basically, in this talk, I discussed the vision of my research in building the algorithmic foundation of fair graph mining. And I have introduced our recent efforts in the quantifying the uncertainty for the auditing task, as well as ensuring individual fairness and the degree-related fairness for the debiasing task. And the open challenges we're trying to solve mainly lie in the safeguarding task by studying the transparency and the robustness of these fair graph mining algorithms. And finally, if you happen to find our research interesting, please feel free to check my website for more details or contact me through email. And yeah, finally, thank you, and I'm happy to answer any questions you may have.
Thank you so much, Jian. That was such an